So this is module 2 of the MREA's Small Wind Site Assessor course, and it covers the material that you will need in order to take the exam, which would get you an MREA Small Wind Site Assessment certificate. You can see here that the material was developed with a partnership with the MREA, Focus on Energy, and 3 really smart people, Mick Segrillo, Sam Simonetta, and Jenny Heinzen. The co-authors are listed here, as well as the reviewers, Chris Talbot-Heindel and also Clay Sterling. These are some of the things that we're going to be covering. Since most site assessors aren't electricians, but a site assessment does have to have some analysis of existing service, we're going to need to determine whether or not the small wind energy system can be interconnected. So in this module, we're going to examine the customer's electrical infrastructure, physically look at it, the billing structure, their load history, and also their primary loads. We'll be making conservation and energy efficiency recommendations. And as an outline, these are the things we'll be covering in this topic. We'll talk about what electrical services are and what infrastructure is. We'll refer to the equipment that connects the turbine to this system as the balance of the system. We'll learn about what interconnections is and how it's done. We'll talk about load history, and we can get that through the utility bill. And we'll talk about the billing structure and some options that may or may not have been considered. And of course, as usual, we'll always talk about energy conservation and efficiency. So most residential and small business services are referred to as single phase. Most of them have a 240 volt input, which gets divided into 120 volts for most of the loads in a residence. Most residences also have 1 or 2 240 volt loads. Now, your larger businesses and farms, it's not uncommon to have a 3-phase power and also to run at higher voltages. So those voltages would be either 208 volts, which can be divided off into 120 volt circuits, or we could then have 480 volts, which could be divided down to 277 and further divided down to derive the 120 volts. So the electrical utility is going to bring the electrical power into the building, which is called a service drop if it's overhead, or it'll be coming underground. If it's buried, then they call that a service lateral. And that'll be coming from a transformer. And we're going to have a shot of that here in just a moment here. Now, the transformer will be rated in kVA, which is similar to kilowatts, kilovolt amps, right? Which is the amount of power that the transformer can handle connected to it. So this is an example of the service connection box that most residences would have. It would be something like this. And as we see here, this is just an illustration. This doesn't represent an actual piece of equipment that's been manufactured by a particular brand or company. So notice here we've got the 120 or 240 volts in here. And notice there's an additional wire here, this ground wire, this neutral wire. Okay, so this particular wire that we've got, if I measure between the 2 black lines, that's going to be 240 volts. But if I measure between either of these 2 black lines and this, what's listed here as the service neutral conductor, that's where I get 120 volts, right? So you'll notice then that this bus bar, right, this is called a bus bar right here, would be connected to this breaker, and we've got this lead here, this black lead, this is going to go out to a branch. And by a branch circuit, I mean one of the rooms or an electrical outlet, or perhaps a lighting circuit. Notice also that there's a yellow wire, and that yellow wire ties up here to this grounding bar, the same place as the neutral got connected. So from this terminal here, the black wire, to this terminal here would be 120 volts. I want to point out now that at the bottom of this bus bar on the left, notice it curves around the corner and hooks up at the bottom, right? And notice that this circuit breaker that's plugged in here has 2 screws on it, where this one up here only had 1. So because it has 2 screws on it, one of the wires or terminals is going to be connected to this bus bar right here, which is connected up here to this main circuit, and then the other screw terminal would be connected to this bus bar, the one on the left. So when I measure between each of these two bus bars, I would get 240 volts. So that means these two wires that would be tied to these terminals would be 240 volts between each one of them, or 120 volts to neutral, either one of them to neutral. All right, so that's how these get connected. It's also interesting to point out here that notice there is an earth ground conductor. I don't care for the labeling here on this. This would be called a grounding conductor. This would be the grounding conductor, whereas this yellow one is sometimes referred to as, yes, the neutral. It's also sometimes called the common, and it's also called the grounded. Not grounding. Grounding is the green one. Grounded is the white. It was this yellow wire. Okay, so, but notice they both tie to the same place. Very interesting, isn't it? Well, this gives us the this provides a very safe connection, so that our 120 volt circuits will have the neutral line be, if it were to accidentally inside of a piece of equipment that malfunctioned, it would, if the hot side of that equipment connected to the neutral side, that would be tied right to ground, and it would cause the circuit breaker to trip. So it's a safety feature. So I want to point out this thing that's called a bonding screw. What the bonding screw does is it ties this earth grounding conductor to this grounding bar to the grounded conductor. So there's a separate screw that has to be in here to actually perform that function. So there's a reference here to the bottom where you can find it's basically the same image. So, but there it is. Now, let's talk about the electrical service itself. So this is the what we would always call the telephone pole down at the end of the driveway or the end of the block, right? And on this pole, we can see that there's 3 wires here, right? These 3 wires have 120 volts going in between each of them. I'm sorry, 240 volts going in between each of them. The 2 bottom ones, and then the top one would be a grounding line. Notice this one up here. Look at that, 13,500 volts. So 13,500 volts comes down into this transformer, and on the output side of the transformer, we can see these 2 bottom lines. That's where we're getting the 240 volts between these 2. Notice that there's a little bit wider spacing on the top one. That is a neutral line. So from either of these 2 lines to the neutral line, I get 120 volts. Between the 2 hot lines, I'm going to have 240 volts. So this is one way that we can do it. Now, if we could see on the side of this transformer, one thing we might see, there's a wide variety of numbering systems that the utility companies will use. They may have it listed on the side what the kVA rating is on it, and they may not. They may also have, if this happens to be a dual voltage transformer, it would be possible that it would have 2 voltage levels listed there. For example, 4800/14,400. So that would be a transformer that was installed knowing that there was an upgrade coming, and that initially this top wire may have been 4,800 volts, but they knew that it was going to be upgraded later. And so they would put a transformer in that had a switch that could then be flipped when this top leg got brought over to the higher voltage. So those are the overhead service, right? So this wire here, this wire that goes here, that's the one that's connected to your home, to the meter panel, to the meter box on the side of the house, and so that's an overhead service. Now this one here, these are the underground transformers, right? You'll notice there's no wires coming out of the top of this. This one here hasn't been connected, right? So when this door gets opened up, like we see here, when it gets opened up, this is where we would make the connections. The high voltage connections would come up through the ground and get connected in here, and then the step down voltage, the 240, would go down to what we called a lateral, and the lateral would go through underground conduit to be connected to the home via the meter base. So again, notice the different numbering systems that are on here. Okay, And some of these are purely marking, so they're put on here by the utility so that they can identify the exact piece of equipment that they're using. So, a couple things. Transformers are going to provide power. Power is instantaneous, okay? And so that's measured in kilowatts. And it's the rate at which energy is consumed right now, okay? Right now. For example, if you've got a light bulb turned on and it's a 60-watt incandescent light bulb, it's using 60 watts. We don't know how much energy it's going to use until we measure the amount of time it's been on. And that we refer to as, or we measure in kilowatt hours or watt hours. So, just a bit of an electrical refresher here. This is the cover of the Uglies book, and this is the Ohm's Law wheel. And we've also included the Watt's Law wheel, Ohm's and Watt's Law. All right, so they're both right here. They work very well. And if you don't have an Uglies book, I highly recommend that you get one because they really, really help you to memorize the things that you would want to know. It's very interesting that we have both volts and watts above amps and ohms, right? And so what's nice here is by covering this P, right? If I'm trying to solve for I or R, if I cover the P, covering power, in order to, if power is what I'm trying to solve for, what's left is I times R. So the math is shown right there. I is next to R, so we multiply the current in amps times the resistance in ohms. And that would give us the watts. Okay. If we wanted to know the volts, right? If we wanted to know the volts, we'd cover the letter E. And what's shown below then is, again, I times R. Right? So E is equal to I times R, just like we thought. Okay. So we can also do it in division-wise. Let's say I wanted to know the resistance, right? If I wanted to know the resistance, you'll notice there's three formulas shown down here. Then we've got resistance is going to be equal to the letter E, which is above the letter I. So here we go. E over I is going to be the formula that I need for this. In the example shown below, they're saying that we want to calculate for the number of watts, right? So if I cover the P, and it says we have 240 volts on the grid times 10 amps of current being drawn by the load, that adds up to 24, or that the product of that is 2,400, okay? And if it were on for 6 hours, we would then multiply that 2,400 times the 6 hours to get us 14,400 watt hours, which is again 14.4 kilowatt hours. So that's just a bit of a review there. This is a drawing that Chris did for us, and it's kind of funny. Chris was working at the MREA a number of years ago, and her background was not electricity, but she's quite the artist. And so here we have one cat providing all the pressure to push the dog through the hole, and the hole isn't wide enough, so it offers a certain amount of resistance, and the fastest we can get it through, the rate at which it goes through is known as the amperage. So this is just sort of a funny take on what voltage is. Voltage is the pressure that causes the current flow to go through a conductor which has a certain amount of resistance. Now again, we talked about service panels before. Electrical services are referred to as main load centers, and that has feeders which can be as subpanels. And so either the services in the main load centers or the subpanels are going to contain either fuses or circuit breakers that are going to distribute the power through what are known as branch circuits in a home or a building. The rating of the panel is determined by the amperage rating of the main circuit breaker. So if the main circuit breaker were 200 amps, it's possible to have more than 200 amps worth of circuit breakers installed in the panel. It's not just as simple as if it's a 200, I can put in 20 10 amp breakers. You can actually put in more because the likelihood of everything being on at once is very low. All right. So if we are going to be able to connect up our wind generation system to an electric service panel, we're going to have at least 2 free spaces for a double pole circuit, meaning 240 volts. Remember we saw in that picture a couple slides before, we saw a service panel that had a breaker that had 2 switches on it. That's referred to as a double pole breaker. So if it turns out that we don't have enough room in our service panels, then it's quite possible that we will have to upgrade the panel itself to something larger. So this is from Mike Holt Enterprises. He's got some great electrical training stuff that the electricians use, and this gives us an idea of just how all these things get put together. So here we've got, this is the overhead connector that came from the transformer. So there's a wire, and it's going to come down through here, and this is the meter base. Notice the ground goes around the meter base. The neutral does. Right? That neutral goes up to a neutral line here. Okay, we can see the grounding conductor up through here. So this is my main circuit breaker. In this case, they have it then feeding this feeder box, and here we have the separate circuit breakers like we'd seen before. This gives us an idea of how this top circuit breaker that's shown here is connected to this side. Notice every other one is tied to the left side, and the opposites are tied to the right side one. And what we have here is we've got 120 volts going into this circuit for this lighting, and we have 120 volts going into this circuit for this outlet. Each one of those is on a separate branch circuit breaker. Notice they share a common wire, neutral wire. So that wire isn't switched, right? The white isn't switched. It's tied here, and then through this bus bar on the bottom, that bus bar ties it back to here. And again, we also put the ground lead in there. So that's what we have. Now notice these drawings over here. Notice that this electrical outlet has a hot, a return, and a green wire that's only connected to the box, right? Well, this is a metal box. Whoops. This is a metal box, and that metal box is acting as the ground, so that all these are grounded together. Notice the bonding wire here. This bonding wire is going to connect the white common line to this box, and then because it's got metal conduit all the way through, that is acting as the grounding wire. Most of the time, they will actually pull a bare wire through here to be that grounding wire. They won't just use the conduit. Even if it's metal conduit, most of the time they will use that grounding wire. So we will have to go into the customer's or the client's building. We will have to do a physical inspection to see what kind of service do they have. What does their breaker panel look like? Are there any spare spots? It's possible that it could have fuses instead of circuit breakers, which isn't necessarily bad or unsafe. It just means it's probably old. If we're going to be upgrading to add wind, we will have to put in circuit breakers and go away from fuses. We'll also have to determine if it's a single phase or a 3-phase, which could be advantageous to the customer. If you knew that ahead of time, that could help you in deciding which turbine to buy. 3-phase turbines are a little more efficient than single-phase turbines. We want to know what the nominal voltage of the panel is. Remember, it's probably 240, but it's possible that it could be 480. What is it rated for? We want to make sure that the system can handle the extra loading that the turbine is going to be adding to this. And of course, we need to know how many extra spaces are there. We're going to have a picture here in a little bit of what some service panels might look like. So a service panel upgrade will be necessary if it has fuses, if there aren't at least 2 empty spaces for a single phase or 3 empty spaces for a 3-phase connection, and if this panel in the main service is rated for less than 100 amps, and it is possible to find some 60 amp services out there, then we'll need to upgrade that. So here are a couple of panels that are going to be requiring an upgrade. Now, if we weren't putting in an extra circuit, there's really nothing wrong with this. It's not the neatest in the world, but this is actually a
we can see that the two hot leads are to the left and the right. This one with the yellow tape on it, that serves as the neutral. This is not a three-phase connection. Okay, this is just split phase, as we would call it, right? And so this yellow wire ends up tied to all of these connections down here, both the white ones that are shown up here and the yellow ones. Something I notice here, what color is that wire on the bottom? It's really hard to see that. It almost looks like it's red. That is not a good idea, to have a red wire connected to where the white wires or the bare wires or the green wires are connected. And this is what a fused panel would look like. This is the main fuses. Those are normally cartridge fuses, and this handle is used to pull them out. This is an old circuit, right? And so it's got quite a few systems, quite a few branch circuits on it, and the different colored fuses are different sizes. So there's a green, and then there's red, and there's blue. More than likely 15, 20, and 30 amps. Notice we're also color coded here, red, blue, and this is also blue, and notice the one that's on the bottom isn't even colored. And up here we've got some higher ones. Can't read them very well. Other reasons we might want to recommend upgrades is if the panel's in poor condition, if it's fully loaded, and if the turbine is rated at greater than 10 kilowatts and the service is rated at less than 200 amps. Okay, so if I've got a great big turbine and a 100 or 150 amp service, more than likely I'm going to need to upgrade that. Your electrician is going to have to do some load calculations on that, and so that really won't fall on you to do that. What you would need to do as the assessor is you would need to write down the model of the service panel and any documentation you find inside of it, which would talk about what the neutral bus overload policy can be. So notice here that the NEC is going to prohibit us overloading the bus inside the panel. If the bus is only rated for 200 amps, we can't have 200 amps being drawn and used by the regular load and then put another 15 or 20 amps from the turbine itself. That's going to overload it. So the report template, again, we looked at that. Actually, we looked at that in Unit 3, in Module 3, which I recorded before I did Module 2. So this is what the template looks like. And the template is going to have a spot where we're going to indicate what the amperage is on the main breaker, who the manufacturer is and what model, what the voltage and phase are, whether it's single phase or three phase. If there are any empty spaces, we want to note that there are that number here, even if it's 0. What the feeder panel amperage is, if it's applicable. Now remember the shot we had before where they had a separate main that then fed over to another panel that didn't have a main breaker in it. That would be what's known as a feeder panel, and we would need to know its amperage, manufacturer, and model as well. Same thing with voltage and phase, empty phases. And we're going to see here in another slide coming up that we want to know how much area we've got for the BOS. And remember, BOS stands for balance of system. So how much space is it? How long on the wall is it going to take? How long is the room? How wide is the area where we plan on mounting this? And how high is the overhead? If it's a crawl space, we can't do it. We need to be at least 6.5 feet. And if we're not, then we're going to need to request a variance. And then we got a spot here to describe the location of the existing service and a proposed location for the balance of the system. So let's talk for a moment about billing and rates. Most of us have standard customer billing, which does not require us to have more than one meter. So we have one meter that measures all the electricity that's being used by the property. Most homes have the same billing rate at the same, it doesn't matter the time of day. So, but as you can see here, there's also a way to do this using peak and off-peak rates. This is a very popular two-tiered scheme in which we have peak hours
for which occur when energy is most needed from the utility. And of course, that would be during the day, Monday through Friday. That's when most of the hospitals and companies and schools and businesses are open. And so that's when the largest demand for electricity is going to be there. And then when everyone goes home, or most places shut down from their first shift, normal day shift operation, the demand for electricity is going to drop. And when it does, that means that the power company is going to have this excess energy that they really don't know what to do with, because they really don't want to throttle back the gas turbine generator or the coal powered plant. They don't want to throttle that back. Those aren't very responsive. Um, so so they end up with more energy that they can use, and it's possible to get on a scheme to where you pay a little bit extra for the peak electricity and not as much for the off-peak electricity. So that can work out really well. It works out really well for solar customers as well. So this is going to be voluntary. There are also peak and off-peak rates that are sometimes used that are seasonal, summer and winter. Some areas don't have a huge heating load, but they have an incredible air conditioning load. Because of that, they'll charge you less money for the wintertime electricity because it doesn't get that cold that often, but and so you could have lower rates in the wintertime than you do in the summertime. Okay, so that's for the amount of energy reused. And notice here, see, this is in kilowatt hours, right? This is the number of kilowatt hours we're going to use. Remember a couple slides ago, we talked about the energy use is measured in watts or kilowatts used per hour. Well, there's another type of a charge that that I don't think any residential customers are using. And this is a thing called the demand charge. And demand is the instantaneous electricity that's being used. So for example, if the first thing that happens on Monday morning at the plant where you're working is that somebody walks in and he turns on all the machines to get them warmed up. So they've been cold all weekend long. They snap on all these machines. What ends up happening is there's a huge draw. There's a huge demand for service from that particular customer. And if it's in a big commercial area, it's possible that there will be neighboring commercial companies that are also turning equipment on at the same time. And what that means is that the utility company has to meet that demand, and so they're going to charge you for that. And so it's noted here that this energy rate is determined by the 15 minutes of the highest demand in a month. Some companies go by the consecutive 30-minute increments in a month. Okay, so and demand charges, we're going to see that here on a bill, what that can be like. So this is a chart that looks similar to what we would see on in the template, but it's actually not there. But so if we put down the current kilowatt hours reading and we subtracted from it last month's kilowatt hour reading, it would show you how many total kilowatt hours you used. And from that, we can multiply that times the cost of kilowatt of energy per kilowatt hour, and we're going to see that for the usage, for the consumption, we're going to pay a little over 12 cents times 1,550 kilowatt hours, so $184. This is the kicker down here, plus standard monthly fees. So again, we're going to have an example of that here in a minute. Now, if you're using peak and off-peak, then we just have to do this a second time. We're going to take the kilowatt consumed at the peak rate of 340 and multiply that now. Ooh, look, we went up to 18 cents a kilowatt hour. And so my peak charges are $61.88. Well, and so that's amazing. Look what happened to the charge for off-peak hour use. Dropped down to 5 cents. So it's less than a third the cost. So here we're using over 3 times the amount of electricity, and we're paying less than a third of what we were paying in the peak rate. Okay, and so when we add it up, it comes out to be quite a bit cheaper. So again, what was our total usage there? That's 1,400. On this one here, it was 1,515 hours, right? So it's the same 1,515 hours, only we divided into peak and off-peak, and look what happened to my bill. It dropped by $60. So
this is why we want to show this to the customer and ask them when they use their electricity. If it's possible for them to shift much of their electricity to be consumed during the off-peak period, then they might take advantage of a billing scheme such as this. So here's an example from We Energies from a few years ago. A friend of mine, Amy T, used this with one of her commercial customers. And notice this particular customer uses a total of 1,237,397 kilowatt hours. That's their total consumption. And it gets divided up into be less than half of that is on peak, a little more than half of that is off peak, right? And so we can see the rates here. They're kind of blocked as far as what the costs were. So and we can also see, let's see, actual on-peak demand. They're showing what the actual on-peak demand was on the 12th of September at 10:15 of the a.m. that we had a 2,000, it looks, I can't tell if that's a decimal or a comma. I'm thinking it's a comma. So they had an instantaneous demand of energy that was the same 2,000. I'm sorry, 2 million. Is that a that's hard to see. I think that's a decimal. Well, I guess if we do the math, if we pull the calculator out and just do the math, we'll be able to figure out exactly what that is, because it's going to be based on. Yeah, here it is. Here it is. Here's the demand up here. So it's 2,475. That's an actual peak demand. And over here we're going to see how they're going to be billing this, right? They're going to be billing it using the number of kilowatts times (1 minus 5 times 0.952 minus 0.85. Okay, so this is their goofy calculations, right? And it comes down to the total consumption for all meters, right? We had the same amounts of meters here, right? But here's the demand charge then. They came up with a demand of 2,511, right? That was by using this ratio of a formula here, right? So this 2,511.2 kilowatts times, what's the rate? Times $1 per kilowatt, right? So that's the customer demand. Now we also have what's known as this on-peak demand. And look at the rate is on this. It's not $1 a kilowatt. It's $10.73 a kilowatt. Wow, that's pretty serious. So just because they turned a whole bunch of stuff on at one time adds a significant amount of demand to the utility company that they by law are required to keep up with. And that's how they can get away with charging us for it. So you can see the consumption was actually pretty low. Consumption was very low. But so the energy used total, the on-peak and off-peak energy, is less than 70,000. The demand charge is almost $2,700. It's almost $2,800. I'm sorry, $28,000. Notice we also have some fuel cost adjustments here. So take some time and look at this. I almost wish these red circles weren't on here. It makes it difficult to read what it says. But overall, how would you like to have an $85,000 electric bill every month? That might make it worthwhile to put in a wind turbine to offset some of that use.